Okay, so thank you everybody for coming to this PhD defense, the final grilling, final moment we have to make him sweat. But this has been a pretty incredible journey for Isaac, going back, I think I said it before, multiple generations. I think you might be the first in your family to attend college, is that right?
Yeah, on my dad's side.
Yeah, and you know, to get to all the way in that route, all the way to a PhD is pretty remarkable. If today goes well, let's see how that goes. You know, Isaac got his first degree in material science and engineering at MIT in 2017, and his master's in aerospace, mechanical and aerospace engineering here at UCSD in 2019, and this is the follow-up from that. He first showed up here inspired by the work of Joanna McKittrick, who you know, was really an incredible professor and researcher leading the way in biological materials. And when she passed away, we were actually in the middle of an expedition to India, where Isaac had been taking his research and the students that he had sort of organized out into the field under the support of funders that he had gathered himself, and with the help of Ramesh Rao, who's also one of our committee members. You know, a PhD is kind of an incredible thing. You learn as much as you can, and then you figure out how to go beyond. And you know, the committee is comprised of people that have bits of information and bits of knowledge that might apply from different aspects of the problem that you're trying to tackle. But really, at the end of the day, what you're doing is completely new and unique, and it takes fortitude and imagination. I think what's been incredible to see in Isaac's work has been that not only has he been able to combine those two forces, but also you know, have this kind of uncanny ability to get other people to help in his work. I know that there's quite a few of you that have supported some of his work in the past. This is a quality that I think is pretty powerful. You had something like 21 undergraduates working around the clock to make this research happen. So what you see here is a testament to all of that, and I'm very proud of that spirit in you. Our committee is comprised of Professor Frank Talke, Professor Ramesh Rao, Professor Rangamani, and Dr. I'm never going to pronounce this right. Evdokimenko, is that right? Ekaterina, yeah. Terrible at that. And myself as co-chair. You know, the kind of combination of these forces came together in that unlikely experience where his original advisor passed away, and I would like to thank the committee for stepping up and coming together to support something that, you know, really was better than some of its parts. Specifically with help from the Qualcomm Institute and Ramesh Rao and also the different departments across the campus that made, I think, this path possible. But ultimately, it comes down to Isaac, and it's easy to turn away at any given moment and say enough is enough. But you know, if you've got the fire in your heart and you've got the fortitude, then you'll see it through to the end and beyond. And I think that's what we're hopefully going to see the results of, the fruit of today. So, without further, well, this is how it's going to go down. We got a 15-minute presentation followed by Q&A, where we all get to grill him as hard as we possibly can. And then there'll be a deliberation of the committee to make a decision as to what his fate is. And I think that upon that time, we'll return and we'll announce that decision. The artifact of all of his research is a dissertation that I think is going to be useful. If any of you need the hard copy, I can pass this down the aisle. But without further ado, I'll get out of the way. And oh yeah, should we turn the lights off? Is that what you're saying?
It's temperature warning. I just read
off. Okay.
Oh, it's okay. Yeah, it's okay.
It's getting hot in here. Okay, well, without further ado, I'm going to pass it over to, well, I would say one last thing. This work is unique in that it's not just, you know, something that is a theoretical problem. It's a very personal challenge that he's taken on that affects people in very personal ways. And to that, I find an inspiration for the function of what engineering should be for, to try to improve lives and try to help those who can't necessarily help themselves. So I'm very proud of what he's been able to do, and without further ado, I hand you over to Isaac.
All right. Thank you, Albert. Yeah, that was a really lovely introduction. Yeah, it really means a lot. It's been quite a journey getting to this point. Of course, as Albert mentioned, I was formally advised by Professor Joanna McKittrick, who couldn't be here today because she passed away 3 years ago. But it's taken a lot of work and perseverance to get to this point. But I'm really excited to finally be able to present my dissertation work, which is on innovating technologies for affordable and accessible prosthetic healthcare. I wanted to thank all my committee members who came here today and all the audience here for your support. Without further ado, I'll begin. And so just to give you, a little bit of background, of course, Albert gave a really good introduction. So I did my bachelor's at MIT, so got a degree in material science and engineering. I did my master's degree here in mechanical engineering, and today is my final defense for a PhD in mechanical engineering. And so these are my publications. The first 5 are going to be what we talk about during the defense today. So those top 5 papers are the ones we're going to talk about today. So to give you a little bit of background into my work for prosthetic healthcare, in 2017, the World Health Organization estimated that there are around 40 million people who have limb loss, the loss of a part of their body. And for those who suffer from limb loss, prosthetic limbs can basically give them their lives back, empower them to, go to work, go to school, have, educational opportunities, and anything you can imagine. But up to 95% of these people do not have access to any form of prosthetic. And this is especially the case in developing countries where there aren't any sufficient prosthetic healthcare options. And the figure is about 3%. Fewer than 3% of people in developing nations have access to necessary prosthetic health care. And looking at amputation, about 90% of major amputations, the amputations that you can use a prosthesis, are to the lower limbs. And specifically, 74% of those are for below the knee amputations. So what you see here in this figure is essentially we have 2 different examples of prostheses, and the one on the left, figure A, is a prosthetic that is from basically like a Western nation, versus figure B is a prosthetic from India, but you can see that they have the same basic components: a socket, a pylon, and a foot. And really, the socket is what I'm going to be really focusing in on today, because the socket is the interface between a patient and the device that they wear. And so essentially, anything you do, anything you engineer has to really emphasize being able to fit onto that patient. And so the sockets are really the limiting factor for any prosthetic healthcare solution. Sockets need to be custom fit to any and every single amputee individually, and they need to take into account all sorts of things. So the shape alone is not enough, but you need to take into account all these different pressure zones where you can have loads, where you can not have loads, and that takes a lot of experience and a lot of professional healthcare, like clinical experience. So this presents, barriers to, accessibility and affordability. Those statistics I presented earlier on how many amputees there are and how few of them have this healthcare is due to these kind of specialized niche occupations that are required to give them that healthcare they need. So with my dissertation work, I sought to answer a few questions. Can we be able to use telemedicine to alleviate some of these issues? can we deliver an equivalent standard of healthcare remotely without requiring patients to go into the clinic? Can we build prosthetic devices affordably and automatically on a large scale, as well as kind of evaluating the safety? Any solution you will have to build, especially with regards to healthcare, has to really take into account safety. And so I was presented with this engineering grand challenge. So it's a huge systems engineering problem where I have, lots of different components going all together. Essentially, we have the fusion of computer science, mechanical engineering, and medicine all need to come together in order to make, any solution possible. And so, I've worked in basically every aspect of prosthetic healthcare in terms of making a system that is feasible. And so, this figure you see here on the left, I want you to pay attention to it because we're going to be using it today as our outline for the talk. And as we go through the different sections of my talk, you'll see, how all these different components interplay and come together. And with that, I want to begin the presentation. So I'm going to give you a more in-depth overlook into digital healthcare technologies, specifically kind of how we're going about transitioning from hand-shaped prostheses in a clinic to kind of more digital design tools, followed by some of my research expanding the accessibility, and that's using smartphones. And finally, the increasing affordability through additive manufacturing, and that's where we have our safety analyses as well. So the current clinical care model, as I mentioned to you guys before, it really is really labor intensive. It really relies on clinician experience. And so what you see here on the left in A is we have a clinician marking and measuring an amputee's limb, really feeling to see, where these pressure points are, where the bones are. Then they'll make a cast of that, plaster cast of it, and essentially they sculpt it. And that's what you see in C and D, is you see these clinicians, they're sculpting it to create, a socket that can fit somebody. And, I hope that you're able to see from these pictures that it really, really does take a lot of work and a lot of skill to make these. And so people have been really interested in how can we do this process digitally and virtually. And so what you see here in this black and white figure is essentially, this is not a new concept, being able to do prosthetic healthcare virtually, digitally. So for the past 30 years, there have been various ideas in terms of how we can achieve it, in terms of designing, building, delivering these prosthetic devices to patients. And so they really have like three basic steps that you need to do. The first step is, you have a person with limb loss, and you need to basically get the geometry of their limb and be able to digitize that. So there's lots of different methods of doing that. I'll go over them later. Once you have that digitized limb, you have to shape it into something that somebody can wear because it's not one-to-one. So you have to do that shaping process. And finally, you have a digital model, and being able to manufacture that in real life. That's the third most critical step of basically bringing it to reality. And so with my work, I basically followed the same exact three-step principle, just with a lot more modern tools. So with regards to the scanning, how you get the models in the computers, I show 6 different methods on here today. The top 3, the top left, we see those digitizers, manual digitizers, really ancient technologies, using styluses to be able to recreate a geometry in a computer. Of course, your more common MRI, ultrasound imaging that is used in medical imaging in hospitals. And then on the bottom here in D&E, we see laser scanning, structured light scanning, and photogrammetry, which are really more versatile in terms of being able to scan any 3D geometry quickly. But for the course of this research, I really focused in on this bottom right one, photogrammetry, which is basically taking photographs and assembling 3D models just from photographs. So the second stage, which is rectification, basically translating those models into 3D, something that can be manufactured automatically, it's a really challenging problem. So I don't go too much into depth with my work, but there's really incredible work like what you see here is a group at MIT, basically taking into account using finite element simulations, thinking about the tissue properties and the mechanics of the limbs themselves, and being able to shape a device and a socket that can be custom tailored to that individual amputee. And so, but the basic process is you take that geometry and then you'll basically wrap it around the existing one, take into account those features. You might trim out a little from the CAD model, and then create something that can be, in this case, 3D printed. And which is, of course, the most common way that people actually manufacture these devices, using additive manufacturing. So you can see here on the screen that basically any type of additive manufacturing technology, people have tried building prosthetic sockets with it. But the most common, and the one that I use in my research, is this top left, fused deposition modeling, which is your standard 3D printing method where you have an extruder nozzle, printing out plastic, and being able to create 3D objects that way. So yeah, with that little bit of context out of the way, I can start going into a little bit more details about my work. So the first section I'm going to talk about is basically, we were interested in using cell phones to basically cross that accessibility gap and be able to take patients into the clinic without them actually having to physically go there themselves. So the telemedicine solution. So there's a hypothesis, which is that we would be able to facilitate these interactions between patients and clinicians virtually using smartphone technology. For our specific aims, we developed a cell phone scanning method to scan, render, and rectify these limbs digitally, and we used photogrammetry. We proposed to use photogrammetry as the foundational technology to make it possible, and that's because it's the lowest cost of all those methods. So here we are, stage one, scanning, in terms of how do we get that patient's limb digitized, get it into a computer, something that we can work with. And so it's a major challenge. And so what we did is we built a cell phone application, and essentially the workflow is quite simple, where you just go, an amputee is sitting down, you mark a little bit of scale to be able to tell how big their limb is in different directions, do 2 passes around it, and then that's it. You send it to the internet and it's done. It sounds simple, but a little complicated in practice. And so this is what it actually looks like. This is what our application actually looks like. And here's it in action. So you'll see it's quite seamless. So with just 2 passes, I think this is just going to go over, maybe 30 seconds. And so just once clockwise around the limb, once counterclockwise around the limb, and you get enough data to render a 3D model of that leg. It's very quick. So, but of course, it's not that easy. I'm not going to really go too much into the details today, but essentially, creating the cell phone application, you really have to really go into the deep with this Android Camera 2 API, being able to figure out how to get your camera system to work, to be able to acquire the data we need. We needed basically a system that could capture hundreds of images in a 1 minute period without being able to crash the device, and also being able to get them so that they're all sharp. Because the obvious solution is to, why don't you just take a video? And in our experience, it's just not possible to get the quality of data that we need. So we needed quality data, high resolution, and we needed it quick. And so, with that data though, with that application, we still needed to be able to turn it into a prosthesis. And so we basically have to render out that model and then turn it into a device that somebody can wear. And so this is our rendering workflow. So in the top left and on A, you can see a limb is basically being reconstructed using photogrammetry. So each one of those blue rectangles represents an individual picture. And so you're able to reconstruct from, if you have two pictures side by side, you're able to compare points and on the image, and then where the points shared, basically you can create what's called a point cloud. And that's actually what you see. That's a collection of basically shared points between all the images, which is the foundation for the 3D model. So you densify it, turn it into a mesh, and then you can work with that. But life isn't that easy. And so one of the things that we had to deal with was that the application that we built it for a purpose, which is to gather large amounts of high quality data. And then what we ended up doing is getting these whole rooms of data and millions and millions of points, and it's completely unworkable. So what we want is what you see on there on the right, just a simple leg that we can work with. So the question is, and here's where we're getting into some of the serious research, is how can we essentially isolate this from these limbs from this scene? And so it's actually quite complicated. And so segmentation is a big problem in computer science. And so I really had to buckle down and think about, how can we be able to automate, the post-processing of our data sets, be able to answer the research questions that we're interested in. And so using deep learning, essentially, we were able to automate the process of removing the backgrounds from our images. So I'll kind of walk you through this slide a little bit. So we have our graphs on the left. And so this graph is basically showing, so the intersection of reunion is basically how well does our deep learning model remove the backgrounds from the images we're interested in. And you can see that as we train it for more epochs, which is just more training cycles, it gets better. And how do you know it gets better? Is we have a loss function, which is the curves you see on the bottom. And those loss functions, basically, we're using a technique. It's a variation of gradient descent algorithms, but specifically Atom. And essentially, when you're doing things like gradient descent, as long as you see our function decreasing, you know that you're optimizing in the correct direction. But yeah, we found that 10 iterations was enough, and any more would be overfitting our models. So, on the right, we can see, we have these images of various limbs from just our collection in the field. So we trained the model basically by creating these masks where we did it by hand in Photoshop, saying, okay, here's the boundaries of what we need. And then basically we had a series of classifiers, which is in our deep learning, deep neural network, which is able to kind of interpret, that data we provided it and be able to do it on its own. And those yellow limbs you see are the ones that the computer came up with. And you can see it did a really excellent job. And we were able to remove the backgrounds. And all that was just so that we could answer the ultimate question, which was, if we use photogrammetry, if we basically do the cell phone scanning with our application, are we going to even be able to have limb models that are accurate enough for clinicians to use and accurate enough for like in a medical context? Because we're basically creating a whole medical scanning technology. And in fact, we do see that. So you see here in this figure down here at the bottom, so our mean absolute error, so we have two metrics, our root mean squared error and our mean absolute error. So in our case, we have some biased results because amputees, of course, are moving their limbs constantly. And so that motion translates into when you're comparing two models, you can see differences just from like a limb being flexed. So that's reflected in the root mean squared error, but to a large degree. So looking at just the mean absolute error, we're at sub-millimeter values for both the mean and the standard deviation, which in the context of scanning limbs is really excellent. You only really need, plus or minus like 2 millimeters or 3 millimeters. So there's no official figure, but the official figures are 10% volume fluctuation. So sub-millimeter is more than overkill. And even our RMS, our root mean squared error values are also very good at 2 millimeters. But you can see that they're slightly affected just by the fact that the leg was moving in our comparisons. So now we know, after all that work, that we're able to get leg models. And so that's our biggest achievement, of course, of that whole thing, is being able to capture the limb geometry, send it via the internet, be able to render it. And then here you can see kind of what we do with it. How you have this limb model, but you have to transform it into something that somebody can actually wear. And this is something that, of course, would require far more work than was even in the scope of my PhD research. There's a lot of great teams out there working on various methods of automating this process, because everything you see here is all someone operating on a computer, using their experience and thinking about how the amputee is going to interact with it. But basically what I want you to see is, how we transform a 3D model of a limb and turn it into something that somebody can wear. So just for a quick comparison, we had a model that was made by a professional P&O clinician, and we went through our whole workflow. I just wanted to see how it compared. And of course, when we're talking about the sockets, there's a lot of subjective kind of things in terms of like the decisions that people make when shaping it. And so in terms of going forward, that's something that would really require a lot of work in terms of how can we go about automating that whole process of shaping the limbs. Because you can see here, like our decisions are very different from the decisions that the clinician made. And so that's something that if you wanted to make an automated process, that would have to be rectified in the end. So some of our lessons were that it is possible to build accurate 3D models of limbs gathered from data from cell phone photogrammetry. Essentially, we were able to use deep learning to increase the efficiency of image segmentation, which allowed us to isolate just the legs themselves. They're within the geometrical margin, that 10% volume fluctuation that the clinicians need. So that was really, really awesome. And then so some of our work that we need in the future, of course, is thinking about that rectification process, about how do you turn that limb model into that final socket shape. That's something that would require a lot of work in terms of thinking about how can you really digitize like all that tactile clinician knowledge and into something that a computer can do. With regards to our deep learning models, making sure it's robust for all races, all genders, all ages, so on and so forth. And then thinking about if you wanted to use this type of system in practice, how would it comply with government regulations such as HIPAA?
Can I ask you a question?
Go ahead. This is a good point.
What do you do if you go to a country that does not have the iPhone that you prefer to use?
So
What do you do then with the software, if the software and the iPhone, the scanning software and the iPhone may not be compatible?
Yeah, so I'll repeat the question since we didn't have a mic on. So the question was, for the cell phone scanning, what do you do in the event that you're not using an advanced iPhone or something that someone that we take for granted in the West? And the answer to that question is actually very fundamental to my research. And so actually the whole reason we chose to use photogrammetry was because photogrammetry could be used basically on any smartphone. And so we basically had $100 cell phone that we purchased because we did a field expedition, and we went into the field and we interviewed people out in India. We're saying, what kinds of phones are you guys using? What kind of budget do you guys have? And so we got one of the phones that they were using out in the field, and we did all our testing on it. So it was all on Android, and it was all on a low-cost cell phone. And so it all worked. And so, because that was something that was really important. So because we figured that if we could build a solution, it was, so much work went into being able to create a solution that could work with the lowest technology point of entry. Because there's so much you can do on the high end, but if you can really raise our foundation, you can reach more people, and so that's what we did with this work. Yes, that's a great question. Yeah, so the final section, of course, is going into increasing the affordability of our prosthetic devices. And that is, we have a lot of different techniques, but really I went deep into thinking about how we can improve the properties of the materials used to manufacture the prostheses, and then also created a system for structural analysis. So bear in mind, we're going to have a little bit of a transition right here into a little bit more. We were in computer science previously, and we're going to kind of go into a little bit more of like mechanical engineering and material science. And so I'll start this video for you. So this is a 3D printed prosthesis that we manufactured here at UC San Diego. And so our major hypothesis was that we could create new materials that could improve the ultimate tensile strength of what we need to print these prostheses, as well as that we could basically create a system that to analyze the structural properties, the strain, the stress, and the displacement on all of our prostheses in order to see not just the material contribution, but the final structural performance of the material in action. And so, so we aimed to develop new composite materials. We also designed and built a 360-degree camera array to do our strain analysis and to evaluate that structural performance. So in our virtual clinic workflow, we're here on the final stage, which is the manufacturing stage. So every stage has its own problems, of course, but this one is particularly difficult because it involves taking that digital model and bringing it to reality. And reality is a lot more complicated than anything you can program. So one of the major problems, as I mentioned before, is essentially, there's a question of the strength, especially with regards to 3D printed prostheses. So people have been actually 3D printing prostheses for over 30 years, but why aren't they really used in clinics on a large scale? And it's just the trust factor, just not being able to trust the device that people are wearing, making sure that the materials are strong enough. And so I used a lot of my material science background and thought, how could we make new composite materials using existing filament materials, and then thinking about the processes that they used in manufacturing prostheses in the clinics, and can we be able to tailor a method of making composite materials that is also compatible with the way that they already create prostheses in the clinic. So I took 3 different polymers here, PLA, carbon fiber PLA, and carbon fiber PETG, and combined them with various combinations of epoxy and urethane. So our PLA basically served as our control, so we can, because there's a lot of literature on PLA, but we were really interested in these carbon fiber added filaments because the carbon fibers essentially change the way that the polymer chains interact. They make it more rigid, almost like cross-linking mechanisms of increasing the stiffness and strength of our polymers. And so we wanted to see, could we make these composites that were stronger and more stiff. And so my team and I basically tested out 18 different material matrix print combinations where we evaluated the materials themselves, looking at different loading configurations for axial and transverse loading configurations, and then of course the materials plus the different epoxies and the different urethanes. And so we had 18 different materials, composites, and you can notice here that these are all sandwich structures. And so meaning that you have our face sheets, which in our case are our filaments, and in a separate core. And our core material is the resin that we infiltrated it with. So we created a whole new vacuum infiltration methodology for basically being able to manufacture our materials. So we were able to 3D print test sheets, but those test sheets basically served as molds, which we then filled with resin using basically, this reads from left to right, where we had a resin, a bunch of tubes, and a vacuum sucking it all through, and things like this resin jacket, and what else? The breather and beater cloth to basically make sure that the resin is evenly dispersed as possible, try to not have so many porosity defects, So we took a lot of consideration in this vacuum filtration methodology. So we also wanted to do standard material testing in order to make sure that our properties conform to ASTM standards, and that, you know, when we analyzed our material properties, that they would reflect the material itself and not like your testing configuration. And here are some of our results. So on here you can see, I guess I should have done this earlier. So right here, we can see on the left-hand side of each of these figures, we have the standard material without any infiltration, and then we have the two epoxy and urethane infiltrated materials. So when it comes to axial loading, infiltrating with either the epoxy or urethane either did nothing or slightly increased it in every case except for one, which is our carbon fiber PLA and urethane, which actually reduced the stiffness. So, however, there's a totally different story when we look at the transverse properties. So when you're 3D printing these materials, they're very anisotropic. So meaning they're stronger in one direction than the other. So the transverse direction is by far and away like the weaker direction, and that also applies to properties such as stiffness. And you can see here quite clearly that in infiltrating with either the urethane or epoxy really increased the stiffness of our transverse direction. So something that I didn't mention before is that our materials, our filaments and our resins were compliance matched for stiffness. And so what you're seeing here is actually, they're much weaker and much less stiff due to the printing process itself. But creating the composites, we're able to regain a lot of that stiffness and reduce that anisotropy. So tensile strength is a little bit more complicated. So in the axial direction, the strong direction, infiltrating with the epoxy basically decreased the strength in every case. However, infiltrating with urethane, actually kept it about the same and actually increased it in every case. So from this point of view, the urethanes are really looking quite promising. And so looking at the transverse properties, we can see that, it's very similar to our stiffness trends. We can see that incorporation of either the urethane or the epoxies into our systems in these composite materials improves the strength, and it's actually quite dramatic, especially for those two, the ones you see at the top, which is carbon fiber PETG and urethane, and carbon fiber PLA with urethane, and it's a factor of more than 5 in terms of the ultimate tensile strength increase. So this really is really good data to show that it is this vacuum infiltration methodology for creating these composite materials actually does increase the strength, especially with regards to the transverse properties, which are the weaker properties. And so, unfortunately, when it comes to manufacturing our prostheses, most commonly they're manufactured this way, with the transverse, because of the way that 3D printers are built. And so, by default, you're manufacturing them in the weak orientation. And so, with this technology and these new materials that we made, we're able to improve those properties in both the stiffness and the strength. But of course, not everything is perfect. In fact, we had almost hoped for better in terms of more dramatic improvements in material strength and stiffness. And so one thing I want to call your attention to are all these defects. Might be hard to see on the screen here, but I'll highlight 2 examples for you in axial and transverse loading. So these are our carbon fiber PLA and filled with epoxy, and you can see in both of these cases there's a huge amount of porosity. By a huge amount, these are like 1 millimeter, so it's very hard to see with your naked eye, but they're very real, and they dramatically essentially decrease the strength specifically. So if you see those lines, I'll mouse over right here, these lines right here. So these are indicating essentially they're hackles, indicating where the failure point initiated from. And so in these materials, we can really see that, our failure is primarily caused by this porosity. So although we try to, minimize some of that porosity in our, infiltration process, in our manufacturing process, it still existed, and it still dramatically decreased our strength specifically. And, so any future research would have to address that. So we were interested in quantifying, in all our samples, what is the true amount of porosity. So those images I showed you previously are a little bit biased, right? Because it's where they broke. So of course, if they're going to break on the pores, you're going to see them in every image. So, but we wanted to see, what was the true amount of porosity in our samples. And so using image J, I was able to quantify not just the area fraction of porosity, but also the average radius and diameter of all the porosity. But yeah, specifically for area fraction, it actually was less than anticipated, so about 0.59% to 4.76%. So it wasn't so bad. It's quite low, but of course, there's different ways of addressing the manufacturing process to reduce that number, just because even a small percentage has such a big impact on our material properties. And so I apologize, there's a lot on this slide, but what I want to draw your attention to is these equations on the left. So I wanted to kind of figure out if I would be able to predict the properties of our materials, so that in the future we would be able to not necessarily have to go through all the different material combinations before finding kind of prospective candidates. And so I used the traditional rule of mixtures just kind of as a foundation for creating, models for understanding the stiffness and strength. And I added two correction factors, our n naught and this 1 minus psi squared. So essentially, our traditional rule of mixtures is if you have a two-phase composite, two materials, you can simply, for axial loading, add up the properties where you have the stiffness of 1 and the volume fraction that the composite is composed of, and add it to the volume fraction of the second material and the stiffness of the second material, and be able to get a material property of the combination. So of course, this is a first order approximation, but adding these two correction factors really allowed me to be able to more precisely predict the properties, but really specifically with regard to stiffness and not so much strength. So what we see here on these graphs, the middle graph is our graph of our modulus. And so all the points that are red, I apologize, the audience can't see it as well. The projector is a little bit dark, but yeah, they're all the ones that are on the very top. And so you can see that's quite far from that line of best fit for your model. And incorporating our two factors in, we're able to improve the prediction. So now, all right, so what are these two factors? So 1 minus psi squared is actually a quite common one. It's the correction for porosity. So we could see in those images, we could see that there was quite a bit of porosity. So there's actually, in the Gibson and Ashley book on cellular solids, they describe different corrections for different configurations of cellular solids. But however, since our materials are very, very dense, they behave more as continuous solids. And so 1 minus psi squared is essentially a very common metric of incorporating porosity. And then this n naught is the Krenschel factor, but I modified it slightly. So the Krenschel factor is a measure of fiber orientation efficiency for composites. So if you have composite materials, you have fibers and you have a matrix. So depending on the orientation of those fibers, you'll have a reduction of material properties where it's, where if it's parallel, it'll be strong. It's parallel to the loading direction, it'll be strong. Opposite the loading direction, it'll be weak. So, but the traditional Krenschel equation basically says that it's, your contribution is 0 if it's loaded transversely, which of course is not true. Our stiffness was not 0, and it was not just the properties of the matrix, and that's because our 3D printed filaments are basically continuous with each other. And so basically I added this factor, which is the A sub n, which is, it's just a bound. It just basically bounds it so that you can never get lower than the transverse properties. So basically just by simply measuring or predicting the degree of anisotropy, you can be able to predict the strength of that filament material. So yeah, anyways, finally, on the right-hand side, we see the ultimate tensile strength. And I was a little bit, I was pretty happy that I was able to improve the properties of the transverse material strength prediction, but still for the axial, it's still a bit off. And so you can see that it's still, of course, just an approximation. So the moment you've all been waiting for, which is, I made all these materials, but can you actually do something with it? Can you actually make a prosthesis with it? And the answer is yes, you can. And so what you see here is a socket that we manufactured before vacuum infiltration. You can see it in the vacuum infiltration setup. And then we cut in half one of our samples to give you an example of, what does it look like on the inside? How is the infiltration going? How does the porosity look? And it looks identical to our materials that we manufactured for our test specimens. And so that reveals essentially that the material properties that we got before from our analyses, we can use that to inform, our design of these prostheses. So going into the final part of my talk, we did all this analysis of these materials, created new materials. Then, of course, we wanted to understand, can you actually use, how do those materials perform in a structure, not just in an idealized loading configuration, but how does it actually perform on the real structure? And so what I built is this 360-degree camera array. Has about like 20 cameras around it. And so they're all connected together via a network. So they're all in a local area network connected via an Ethernet switch. So basically, we're capturing synchronously videos in 360 degrees, which we can use for a technique called digital image correlation. But here's the simplified schematic of that network configuration, where we have a control PC controlling, communicating with the network. All those computers are all synced with each other versus with something called the network time protocol. And then that we have a master, basically clock, that's synchronizing all of the cameras together. And so what does this allow us to do? It allows us to go and do this technique called digital image correlation, where if you have these spots on the surface of an object, known as speckles, you can basically track that pattern over the course of a deformation cycle and be able to analyze what is the strain or the displacement on the surface of a sample. And so we built a system that we could do this digital image correlation in 360 degrees all around the surface of a prosthesis. And that's what you see here on the right in this load frame. And so, this is just showing how our test specimen in this case failed. Is a delamination failure at the bottom. And so, but of course, things are not as easy as you think. Even though we built that whole system, we also had to build the software to analyze the strain data. So we were building off of an open source package from MIT called Multi-DIC, and then basically we created a automated way of doing that strain processing using the algorithms the MIT team developed. And what you can see here is we were able to reconstruct, you can see in this one too, in 360 degrees the socket, and we're able to get the actual true strain on the surface. So we compared those to some multi-body finite element simulations that we had done, and of course one of the things we noticed right away is that our simulations were off by an order of magnitude compared to our experiments. And so really, what I want you guys to see from this is that using that technique that we developed, we were able to see a problem that if you had only done simulations, you might have thought it would have been safe, but a factor of 10 is a factor of an order of magnitude when it comes to safety. And so it's something that is kind of an unacceptable margin. So my hope is that these kinds of tools will be used more in the field of prostheses for this type of safety analysis. So coming to the end, so what are some of the lessons we learned? So we were able to develop new composite materials that increased the ultimate tensile strength and also reduced the printed anisotropy. And that was specifically with those urethanes and the carbon fiber filaments. And in addition to that, we were able to build a whole full field 360-degree system for mapping the strand on a prosthesis and to validate the safety of the prosthetic designs. So there's a lot of future work. The materials we developed, had porosity that could be improved by optimizing manufacturing parameters. The tests that we did, of course, were quasi-static, not dynamic. So walking is a dynamic process. So you really need to have dynamic tests as well. And then, of course, any lessons that you would learn from that, you have to be able to generalize that because every single socket is patient-specific. So being able to take that and make bigger design decisions in the future, you really have to do a lot of tests to be able to generalize those findings. So in summary, here's the questions I kind of posed at the beginning of some of the goals for this research, which was, can an equivalent standard of care be delivered remotely? And yes, so we were able to connect patients to clinicians using cell phones and cell phone photogrammetry. Can we build them affordably and automatically on a large scale? So we really made huge strides in this automation process in terms of being able to render those models automatically. There's still a lot of work to be done for the rectification itself, but in terms of being able to scan and transmit all these models via the internet, the huge strides, and we're able to do it now. And in terms of the safety, how safe these prosthetic devices are for human use, we developed new composite materials and a whole testing methodology to analyze it and the safety of the structures in practice. And with that, I'd like to just thank all of the colleagues, contributors, supporters. I realize I've been using the we a lot, and that's because really I couldn't have done this work alone. So I've had 21 students work for me, and they've been some of the most dedicated people I've ever met. Just everyone. I just want to thank everyone in the room here. It's really been great getting to this point. It's really incredible experience, and so now it's time for questions. Thank you. So how this is going to work is if anyone has a question, if you could raise your hand, and we have a microphone because the people on the broadcast will not be able to hear you. And so we'll pass the microphone. And I know Marc is on the call, and so we're not going to be able to hear from Marc until the private deliberation period because I'll have to unhook this setup so that you can hear from Marc.
We should start with committee questions. If there's any questions from the committee.
Thanks, Isaac. So I have a very philosophical question.
Mm-hmm.
So you made the case that digitization is important.
Yeah.
Is it? I mean, there's a huge assumption there, right? I mean, this is, after all, a degree in Doctor of Philosophy, so let's...
Yeah, I mean, that's a great philosophical question. Yeah, and I think, yes. So the point of digitization is not so much to replace the clinicians, right? But really to be able to help them to reach more people, right? Because one of the biggest problems is there's a limit in terms of how many people you can practically train and how fast you can train them in order to be able to address the problem, right? It's a huge scale of a problem, but you might have only maybe a few thousand of these clinicians across the entire globe. And so, if you have 10, 20,000 clinicians, you're not going to be able to practically service 40 million people who need these devices. And so the goal is, to be able to provide them with additional tools to reach more people. And so I think from that point of view, what they do with those tools is their decision. But if we give them the platform to succeed, we hope that they'll be able to succeed.
Thank you.
Very nice presentation, Isaac. Very exciting. I have the following question, and it's in a way probably far out, but
Oh, it's okay.
you say these composite materials have always some problems and have strength limitations.
Yes.
And you know that in the last few years, it has been possible to 3D print metals, like titanium. Those printers are, of course, extremely expensive. We were recently at Innovative. They have 5 of those titanium printers. They cost each $1 million. But for just seeing that whether it would be possible to print a metal prosthetics and whether it would have the strength properties and the elasticity properties that one would need, maybe that would be great, because maybe in 10 years it'll be, or in 5 years it'll be feasible to have metal printers that we don't even know about today.
Yeah, so I do have an answer to your question, and so actually quite a few people have looked into creating metal 3D printed prostheses. So I wrote a review paper, which is the one that you kind of see behind me. And in that review paper, you know, selective laser sintering is the main one that people use for the metal 3D printer manufacturing. And so yes, they have made metal prostheses, but more commonly than creating the total prosthesis for the socket, they'll create something that's called, it's kind of like a cage to hold it, because the shape of the limb changes so much. Even within, you know, a 1 week period, 1 month period, you have those huge volume fluctuations. So printing in metal, you know, although you might have the good, you know, strength weight ratios, you might have the good safety, it's just the flexibility for change and for modifications is not there. So that's why, you know, for 3D printed, the thermoplastics are really nice because you can remold them. You know, with the composites, that remains to be seen, right? Can it be done? We don't know. But in terms of, so like usually for the 3D printing of the metal prostheses, they'll have a combination of the metal frame and a polymer component. And so in terms of being able to reach people at scale, that's hard to say, you know. But is it a good idea? I think in many cases it is a good idea, just in terms of being able to specifically reduce the weight, so you could focus more on comfort and, you know, have whatever you need for the comfort. If there's a weight trade-off, then you can, you know, focus on adding more materials for that comfort. Yeah.
For this, inspired the FEM software from Altair would probably be fantastic to use. And like you said, then you could mold the rest together so that you have also a composite material.
No, and that's, you know, there's another research group here at UCSD who they did just that, and it was a really excellent paper. I think it was just published this year. Where so it's a little bit different than what you're suggesting. So I think what you're saying could be utilized in future research. So because they did use that topology optimization to make a one-piece prosthesis, but specifically with regards to making it a cage and optimizing the cage, you know, I think that could be something that would be really promising. Yeah. So, go ahead.
So Isaac, I had a couple of questions. This one is on your slide 33.
All right.
The vacuum infiltration methodology.
Yes.
So the question I had was, what is the effect of the duration of time for which you let this infiltration process run? Does that affect the final outcome?
Yeah. So that is a great question. So essentially, you're limited by the curing time of the polymers that we used. So because we use two component resins, where you have a resin and a hardener, and in our case, we were looking at, you know, which resins, you know, were both compliance matching, but really we're looking for the strongest ones, with the strongest ones we could find. And you know, those particular formulations had really quick kind of setting times. So because what you would do if in different composite processing is, yes, you would actually probably use a vacuum and try to pull out as many bubbles from the resin before you infiltrate it. So we did that with our resin, but when you mix the resin and the hardener together, you reintroduce the air bubbles. And but unfortunately, we had, you know, lives, what they call the pot life of the resins, between 20 minutes and an hour. And so within that time frame, there isn't enough time to extract all the air bubbles before infiltrating it, because the infiltration takes about 5 minutes. So, but yeah, I think there are ways of improving it, things that we didn't look at, such as, what's the effective vacuum pressure? Because we just used the one fixed vacuum pressure as kind of recommended by the manufacturer, but we don't know how much that could affect how it pulls through. In terms of anything else, there are definitely ways of improving it, but for the lifetime of the polymers, it is a limiting factor. Yeah.
Okay, very good. So slide 39, I had another question.
Go ahead.
It had to do with this mismatch between is it 39? Maybe not. The mismatch between the simulated and the measured.
Oh yeah.
What slide is that?
Yeah, that's I got it. It's this 47. Yeah.
So what would you attribute this to? Are there incorrect implicit assumptions in the simulation?
I think there are some incorrect assumptions. Certainly, one of the main ones is that we assumed that our bodies are in perfect contact of our prosthesis, versus we know that's not true, because that's the whole point of doing the shaping on the interior of the prosthesis, is so that you can have zones that are loaded specifically and zones that are not loaded specifically, whereas here it's in the simulation it's being loaded all around. So our assumption was, it won't be a big deal, it won't be a problem. And of course, it might not be the assumption that broke the simulation, but it is one of the possibilities, that one of the things that could have broken it. Just, one of the incorrect assumptions.
And so in the experimental setup, you had a real
so
model of a stump
so we had
pressing down. Is that what you had?
Yeah, that's what you see here. But in the simulation, they're not loaded. There's slight gaps, of course. And of course, the influence of those loading zones is probably more present in here than in the simulation.
Just real quick, what was the material you used to simulate the stump physically here?
So the one that you see on the image here, we're using our PLA, just our control. So we weren't able to expand out to all our new composite materials to see, so we were just doing our control specimens, our PLA, and so that's what you see in that image there.
Well, look, this has been an incredibly diverse defense in terms of topics, right? Your research has spanned a lot of different aspects of engineering. It started out with a map of the structural engineering challenge that you took, really, which was a design challenge. And then we traveled with your students to India to do field research in a context of Jaipur foot. Can you talk a little bit about how, or if any, or what you learned about your design assumptions going into this from being in the field? Is this a solution that you actually see being harmonious with what is actually happening in places like Jaipur foot, where they are servicing amputees from around the world or from around India?
That's a great question. I think, because I would say that going on the field expedition really kind of, definitely transformed a lot of those implicit assumptions in terms of how you would, what technologies you think that they have, what are they capable of, what is practical to be used in different contexts. And one of the things that I saw that they had in the clinic, or ways that that some of this technology could be definitely implemented. So certainly the self-lens scanning, I think, is very, very much so. So they're very interested in terms of all the 3D modeling technology and being able to be able to 3D print the prostheses. It's not used in the clinics, but even in India, they're really interested in 3D printing of these things. And so from that context, that's kind of universal around the globe in terms of the people who have the capabilities of building the prostheses. So with the composite materials, that was something that was really a big consideration. So that is something that is very feasible in America, but might not be feasible elsewhere. So, because in America, a lot of P&O clinicians, they make the carbon fiber layups quite often, fiberglass prosthetic sockets. They make them out of all these different fiber reinforced composites. So they're used to vacuum infiltration. They're used to using that bagging. They're used to that kind of stuff. But that wasn't really something that I saw in the Jaipur Foot Clinic. So the advances in the 3D printed materials and the 3D printed composite materials really would impact, the United States more, at least at first. So there would be some time delay. Not so much for the scanning, but certainly for the manufacturing. I could see there could be some limitations.
How about from the patient perspective?
Yeah, I think that's something that, you would have to do a large scale kind of case study to see how do patients actually react to it. Because, in our limited studies, a lot of the patients were kind of more curious of, what we were doing, especially with the cell phone scanning. But really, if you want to impact patients, I think the more work would need to be done in terms of making sure that, so if it's a patient's first prosthesis, it has to be done right. Because if you don't do it right, they could be basically sworn off from prosthesis for the rest of their life. And so that's a big responsibility. And so you want to make sure that it's going to work, right the first time. There's no second chances when it comes to that.
My final question is, can you give us a comparison in terms of cost of the prosthetics that you made in the end versus what would you buy in a clinic today?
I appreciate that question. I didn't have room to fit it in my talk, but it's a very relevant question, and it's actually here. It's like how much do these cost? That's the big question. And so here in the United States, for a prosthetic socket, something that would provide you a minimal function being defined as say like going from the couch to the kitchen and back to the couch. That's minimal function. You'd be looking at like $5,000 to $7,000. For a prosthetic device, that would give you more capabilities, being able to run, being able to go outside, go hiking, for instance, $12,000 to $15,000. When you go into details about a lot of what other prosthetic researchers do, which is a lot of computer-controlled prostheses, a lot of robotic components, a lot of that kind of stuff, your price really skyrockets. And that's actually what you see here is over $50,000. So that's really one of the main reasons why I emphasized on using these digital technologies to increase the accessibility, is because a lot of the emphasis in the kind of the research world today is how do we make the prostheses really exciting and have all these functionalities with, all the robotic components. But, the fact is that, the standard of care is very good. It's not perfect, but, having a limb really is a life-changing event versus not having a limb. And so the price threshold that we're looking at in different countries, especially developing countries, is something like $100. And so being able to build like this whole device, especially the socket, for less than $100 is really kind of the goal. And so with our 3D printed materials, that is part of the material selection of why we chose the materials we did and the composites that we did, was to make sure that it was less than $100. Yeah.
Thank you. Anything else from the committee?
Yeah, one more question. Yeah, I have one more question, Isaac, and it's just because we all are interested in your work. When you study the material reliability and fracture mechanics, you have to say that actually there is some cyclic loading, and one should probably at some time also look in cyclic failure of these materials.
That's a really good point. I did mention cyclic in my for the structural analysis, but really you also need it for the standard material analysis too. So
and it's not meant to say you should do that, but I think in the future it should probably be looked at in addition to the stress with the instron, the failure analysis.
No, absolutely.
To do the cycling.
It's right, because especially with composite materials, the likelihood of it failing at a level below these stresses that I reported today are really high, just because of the composites are just more likely to have more defects. Anytime you have two materials that are not the same, anytime you have an interface and you have an imperfection, there's always going to be something that can cause a problem. And so under cyclic loading, you really could have a failure at a level much lower than anticipated. So
one more important parameter, and that is the environment and the environmental temperatures.
Yeah.
Because if you go in the snow or in the desert, then these material properties under these extreme conditions.
Yeah, that's where the carbon fiber, PETG specifically, is really one of the more robust to environmental conditions, versus your standard PLA has tons of environmental degradation. And so it's really not meant and should not be used for this purpose. But for me, it was an effective control because there's a lot of literature. So I could see if the mechanisms that I was interested in improving held true for controls. But you're right, yeah, they're really not suitable. But the material of the urethane PETG composites really could be used, yeah, because they're really highly resistant.
Anything else from the committee?
We should ask
I think we
the
can
audience, yeah.
open it up a little bit. Anybody have a question for Isaac? I see something way down there.
Hi. How long, can you hear me?
I can hear you. Yeah.
Okay. I guess how long would you envision the whole process taking? I guess starting from, the start of a clinician working with the patient to scan the images, and then eventually getting the prosthetic, and then eventually, working with it. And then from there, the iteration process of refining it would also take some time. And going from there, how long do you think, how durable over time would it take?
Yeah, so I'll begin to answer that question. So we do, and I didn't show any slides for that information. I don't have any backup slides also with that information, but we did quantify how long it takes for all the different steps of the process. So for the scanning, the different scanning technologies that I presented on that slide all have different times. So photogrammetry, so the biggest bottleneck was that image segmentation part. So the image segmentation portion could have taken, hours, like 50 hours for one patient, an incredible amount of time. So now basically with the work that I did, we're able to, shrink that down so that it's 1 minute to scan a patient. So that's it, 1 minute. So they send it to the internet. That's a factor you can't control for, right? What their internet speed is. Their internet speed is whatever their internet speed is. But when it comes to processing, for the model rendering, it's basically all automated now. And so it may be 5 minutes of human involvement to make sure that everything's okay, and then everything else is automated. Where there's the amount of time that we didn't improve, which is the shaping process. So that's something where there's lots of room for improvement. But for us, we would take about 3 hours to shape it digitally, which is comparable to kind of in the clinic. They usually take about half a day for an individual patient to shape it. That's just for the initial shape. There's lots of sessions that are usually follow-up sessions, but so you can say that's 3 hours of at least of human time that's needed. For the manufacturing, if you're able to just 3D print the prostheses directly, there's no human time other than taking it off and then assembling it. Maybe an hour. But with the composite workflow, that does add a lot of time. So your human time is maybe an extra hour is added. Then you have to wait an extra day for it to cure. So if you were to use every single piece of technology I showed in this presentation, it would take a little more than a day, probably 2 days. But of course, even under the best circumstances, in the clinics, they don't really try to rush these things. But as long as it's not taking a week or a month, like on the order of 1 or 2 days, is okay.
Any other questions?
Thanks, Isaac, for your talk. I have a couple questions about the scanning process.
Okay. Yes.
One was, do you put constraints on how the scan should happen? So you mentioned a minute.
Yeah.
Should it not be less than a minute? And is there a certain distance that you found was optimal?
Yes. So, so it is optimized. So there's several papers that kind of use like 30 centimeters as a good length for close range photogrammetry in terms of making 360-degree movements. And so our application is kind of based off that. So thankfully for like the analysis of limbs, we're able to get, basically any major limb within that frame. So in terms of the scanning time, you really shouldn't try to go faster than 1 minute. And that's because of things like the camera shutter speed and the camera as gain and that kind of thing. So if you are going way too fast, because we are taking photographs, the camera's not going to be able to catch up because the shutter speed will be too slow, it'll be blurry. So the application we built basically had lots of redundancy built into it. It's actually beyond redundant. It's called hyper redundant, so because you might need 30, if you had a perfect scenario, you could reconstruct a limb with 30 images. So we're usually capturing about 300. So like 10 times more than you would need. So, sorry.
Oh, yeah, and then I think that's the perfect lead into my second question, which
Yeah.
was like the choice of 2 revolutions would not, more and more redundancy add to the accuracy, or did you find that there is that trade-off?
So there is kind of a plateau in terms of the accuracy, and that's right around 90 images. But essentially with the hyper redundant approach, so because when it comes to these kinds of scans, it's usually you just get one chance, and so you don't want to because there's going to be some delay between the scan and it being sent to the internet and being rendered and all that kind of stuff, and so you don't want to a day later find out that you don't have enough data or it's not going to render. So because that if the case is that the patient doesn't have the app on their own phone, someone else scanned for them, which is a likely scenario, then you can't rescan them twice. So you really need to get it on the first try. Yeah.
Great, thank you.
Hi, Isaac. Pretty awesome talk. So I noticed that all of the materials you used were rigid thermoplastics.
Yeah.
Have there been any considerations into like flexible or deformable materials such as like TPU for possible like distribution of stress points and stuff like that?
So I personally did not consider it, but there have been other researchers in the field who've done it, and if you'd like, I can go back to that slide where I show the different 3D printing technologies. There's 2 on the bottom. I can go back for you.
Thank you.
Apologize, it's a lot of slides. We're going all the way back to the beginning. Here. There's various researchers working on different multi-material solutions, and specific to what you're describing is kind of a lot of kind of like compliance matching. Like researchers are kind of interested in, can you have more flexible areas that are a little bit less stiff, especially in non-load bearing places, and so what you see in this bottom left. I don't remember the specific materials that they used, but they did use that concept. So it was one of the things I did think about, but really when it came to choosing the materials, it was really a kind of a trying to optimize for that cost, for that accessibility, and where we thought the biggest improvements in terms of the strength for the overall thing or the overall structure could be obtained from. So that's kind of what went into the material selection process.
Thank you.
I have at least time for one more question before we deliberate. Anybody? Really tough one.
Okay.
Yeah, so was there?
Oh, there's a
Sorry,
mic.
go ahead.
Yeah.
Oh. Was there a comparison between, the strength of your materials versus like the standard what's being used now?
Yes. So what's standard? I don't have a direct comparison No. So in terms of strength to weight ratios, so the weight is usually about the same between our composites and that, but the carbon fiber traditional ones, carbon fiber infiltrated ones, are much stronger, much stiffer. I'm trying to think of the exact number, but the ultimate tensile strength is usually about 3 times stronger. So we were about 20 megapascals, 20 to 40, and they might be about 60 to 90. And so it is stronger, and that's what you'd expect from something like a carbon fiber infiltrated laminate. But for, in terms of 3D printed prostheses, of course, ours are, above and beyond for where that technology is currently. And of course, not all prostheses that people wear are advanced composites. On our field expedition to India, we found out that all the prostheses they make in the Jaipur clinic are all high-density polyethylene, and so the tensile strength of that is actually quite low, relative to what we were doing. So it's about the same. But how they addressed it is they just made them really fat, really thick, really heavy. So they're not optimized for strength or to weight. So they're heavy. But in terms of comparing to other plastic prosthetic sockets, they're pretty good. They're not exceptional, but they're better than the current standard.
Okay, thank you.
Mm-hmm.
Great. Well, I think in the interest of keeping everything on time, we
Yeah.
can deliberate in this room because of one of our committee members being on Zoom. So at this point, is that right?
So I think what's going to happen is we're going to excuse the audience.
Yeah.
And then we're going to stop the broadcast. And that includes the people on Zoom. We're going to kick everybody out from Zoom. And so that way we can hear Marc, who is on the Zoom. I know he's been patiently sitting there quietly this whole time. Now I'll get to hear him yell at me. So.
And then for those of you who can, you can get a drink or something on the way out. But for those of you who want to stay after we deliberate, we're going to invite everybody back, and then it'll be the thumb up or thumb down.
It may take 10,
Yeah.
5 or 10
Who knows? Who knows where we're going to go with this? Yeah. Who knows?
Yeah. So let's stop the broadcast.